All right, here's the next question I was asked about. It's 9C number 4. So here I'm going to draw a picture of this problem. Again, remember you might have different numbers in your problem than I do, but I'm going to do it with these example numbers. Okay, so we've got a rod that's attached to a wall by a hinge at its base. So I'm going to draw that here. So I've got my wall. I've got a rod here that can rotate around this point where the X is. Okay. The rod has a mass of 6 kilograms. Its length is 2.3 meters. Oh, and I should have read the rest of this description before I drew it. And it's at an angle of 25 degrees above the horizontal. So let's fix this picture. So we've got a rod here. It's an angle of 25 degrees above the horizontal. 6 kilograms, 2.3 meters. And then it's held in place by a horizontal cord that I'm going to draw in red, like this. Okay? And it's bolted to the rod up here. All right. And the question is, what is the tension in the cord? Okay. So this is a static equilibrium problem. And so as usual, we want to start by drawing a free body diagram with all forces labeled, and then we will use them to calculate the torques around a point of rotation that we can choose. So I'm going to draw this again a little bit bigger down here. 25 degrees here. I've got the mass of the rod times G. I've drawn that force as acting at the center of mass. And then I've got my tension force. And those are the only two forces on my rod, except for, sorry, also the force from the wall. So then we've got force from the wall on rod. Now, it's not that obvious what the direction is from the force on the rod from the wall at this point, so I'm not going to draw. Well, I will go ahead and draw it at just show that it's got to be up and a little bit to the right. Okay, but exactly which angle it's going to be, I'm going to draw it with a highlighter, so I don't know exactly what angle. So it's something along those lines because it needs to cancel out gravity and that tension force so that the net force is 0, but we don't know exactly what direction it is, so we're not going to draw it very well now. Okay? All right, and now we're going to start by finding the net torque and setting that equal to 0. So it's the sum of all our torques. And we need to choose a point of rotation. Natural point of rotation is here where our hinge is, right? Okay. So we've got two torques here. We've got our torque from our rod and our torque from our tension. So if we think about just our torque from our rod, we've got the distance from the rod to the center, from the hinge to the center of mass is half the length of the rod. So that's 1.15 meters. Our gravitational force is down right here. So our torque from the rod is Fr sine theta. So let's see, we've got our rod, or our radius vector. Radius, remember that's our radius to our axis of rotation, which is here. So that looks like this. Then our force vector is this one. So this is our angle theta here. Now, notice that is not the angle that we were given. The angle we were given is 25 degrees. Apply our good old trigonometry and find that theta is 65 degrees. Okay, so the torque from our rod is Fr sine 65 degrees. And now we haven't talked about the sign of the torque yet. This torque is a clockwise torque. It's tending to rotate that rod clockwise, which is negative for torque. So this is our torque from our rod. Okay. Now we need to find the torque from the tension. So here we've got the whole length of the rod and the tension force here. So now this is our R. Our R is 2.3 meters. Theta here is now this time it is the same as this 25 degrees. Okay, so those are opposite interior angles, which are equal to each other in geometry. All right. So our torque from our tension is the force from the tension, which we are finding. We don't know that yet. Times this distance r, which is 2.3 meters, times sine of 25 degrees. And again, we need to think about the sine of that. So that is tending to rotate the rod counterclockwise, which is a positive torque. So we're going to just leave that the way it is. Okay. Now, we're going to see if this is enough information to solve for our tension, and we will find that indeed it is. So we've got T times 2.3 meters times sine 25 degrees minus our force from our rod, which is the mass of the rod, which was, sorry about that, 6 kilograms times 9.8 meters per second squared, times our radius, which is 1.15 meters, times sine of 65 degrees, and that equals 0. And that is going to give us, when we plug in numbers, that our tension is 6 kilograms times 9.8 meters per second squared times 1.15 meters times sine 65 degrees over 2.3 meters times sine 25 degrees, and that is a tension of 26.4 newtons. Okay. All right, now the second part of this problem is find F wall on rod. Okay, so we know that not only is our torque net equal to 0, our F net is equal to 0. So let's write each of these forces as vectors, which we've kind of drawn on our diagram, but we haven't drawn explicitly. So our force from gravity on the rod is 0, negative m rod g. Our tension force is negative t, 0. Negative sign because it's in the negative x direction. And our F wall then is going to be T M rod G, because they need to sum up to 0. Okay. So our force vertical is mass of our rod. Oh, I think I did make a mistake here. Sorry, I was copying down this without actually doing the math. This is not the right number for the tension. Excuse me. Let me plug those numbers in again. 6 times 9.8 times 1.15 times sine of 65 degrees over 2.3. Okay, so correction, this is 63 newtons is the tension force, and then our vertical force from the wall is negative mass of the rod, which is 6 kilograms times 9.8 meters per second squared, which is 58.8 newtons, and our force horizontal is 63 newtons. Okie doke.